Howdy doody. We have seen how we can use the first derivative test to determine if critical numbers gave us local minimum or maximum values, or neither. Today, we're going to explore the second derivative and see how that will help us classify critical points as well. Now, I want to consider a couple of similar but different graphs. Here we have two graphs of functions, and both of these graphs are increasing. Both of these functions are increasing as we move from the left to the right, but they are increasing in different ways. This first one kind of looks like it's part of a parabola that's opening upward, and the second one kind of looks like it could be part of a parabola opening downward. Now, they're not necessarily parts of parabolas. That's just one way to describe how they're curving differently. Another way is to look how the tangent lines to the curve end up going. I'm not going to be able to draw these beautifully because I'm doing everything by hand. But for the graph of f, all of the tangent lines were below the curve, and for the graph of the right, all of the tangent lines are actually above the curve. So that is another way that we can describe the difference between these two curves. And we have terminology for both of these situations. If a graph lies above all of its tangent lines on an interval, like we see in this first one, then we call this concave upward. It's kind of like a smile in a sense. And the other one, if we have a graph lying below all of its tangent lines on an interval, we call that concave downward. And it kind of looks a little bit more like a frown. So these are two different ways that part of a graph can be curving. And remember, both of these functions are increasing on this interval. So this doesn't have to do with whether it's increasing or decreasing. It's how it's increasing or how it's decreasing. We could also have examples where a function was decreasing and concave upward, could look something like this, and decreasing and concave downward would look something like that. Those are just very rough sketches, just so you can see this isn't just with things that are increasing, could be increasing or decreasing. And because it doesn't matter if it's increasing or decreasing, this doesn't have anything to do with whether the slope is positive or negative, or whether the derivative is positive or negative. In both of these situations that we looked at, the slopes of the tangent lines were positive, which meant the derivatives were positive. What this has to do with is actually how the slope is changing. And since the slope corresponds to the rate of change of the function, and we're looking at the rate of change of the rate of change of the function, this is actually corresponding with the second derivative. So whether a function is concave upward or downward on an interval is going to be related to the second derivative. We're going to look at that in a moment, but what I want to do first is look at another graph and try to see if we can tell where it's concave upward and concave downward. All right, here is a rough sketch of the graph of a function. It is not perfect. None of my graphs are perfect. I'm doing them by hand on the iPad, and the Apple Pencil is a little bit slippery, but we're going to make the best of it. And so if we say that the function starts at A, let's look and see if we're concave upward or concave downward at first. And so remember, concave upward kind of looks like a smile-ish, whether we're increasing or decreasing. The tangent lines are below the graph, and then concave downward looks a little bit like a frown. Tangent lines are above. If we look at the tangent lines at first, they're going to be above. So that's concave downward. It does kind of look like a frown a little bit. But then where does it appear to change? It looks like it appears to change somewhere around here, We'll call that B, right? It definitely looks like a frown at first, but then it turns into a smile. And if we were to draw in some tangent lines, they would be below the graph. So we're smiling for a bit. So it's concave upward for a bit until maybe around here or so. We can call that value C. So we've got concave downward and then concave upward for a bit. And then we can definitely see there's going to be a change at that sharp point. We can call that D. It looks concave downward there. All right, now again, we've got another interval here, and it definitely looks like a smile all the way up until there. So we can call this X value E, and this definitely looks concave upward there. And then in the next bit, it still looks a little bit like a smile until we get right about here or so. That is where it's changing concavity. We can call that F. And it's still concave upward on this interval. We've got two intervals next to each other where it's concave upward with a sharp point in between. And then the last bit, we are concave downward. So that's just taking a look at the graph of a function and trying to see where it looks like it's concave upward and concave downward. Now I've drawn in the points where it changes concavity between concave upward and concave downward, and we have a name for those points. Those are called points of inflection. All right, a point P on a curve, y equals f of x, is called a point of inflection if f is continuous there and the curve changes between concave upward and concave downward. So we can see, for example, that the point on this graph that has an x value of b, that is a point of inflection, or an inflection point, because it changes between concave downward and concave upward. C is also an inflection point, changes from concave upward to concave downward, so is D. E does not count as a point of inflection because it stays concave upward on both of those intervals, but then F again is a point of inflection because it changes from concave upward to concave downward there. It's basically where it's changing between smiling and frowning, if we want to try and think of it in a sort of a basic way. Now, we've said a lot about concave upward and concave downward intervals, and I mentioned that they have something to do with the second derivative, but I haven't made that connection yet. I'm going to stop this video and put that in the next one because I think this is a good place to kind of break them up, and I want to spend the next video looking at when a graph is going to be concave upward or downward based off of the second derivative, and how the second derivative might inform us if a point that comes from a critical number is a local maximum, a local minimum, or neither. So we're going to see all of that in the next video.